All right. Welcome everyone. My name is Raul Marquez. I am the secretary of the UT Austin ECS chapter. And today I will show you a couple of ideas and guidelines on how to create more compelling graphics and figures for scientific publications. So I will discuss briefly different topics here so you can improve your graphics. Well, we'll discuss about the differences of different type of graphs, schemes, and diagrams, and also I'll give you some guidelines on how to do your figures in a more systematic way. I will also guide you on different advantages and disadvantages of using single and multiple panel figures. We'll discuss about figure captions and also how to improve the table of content images. We'll talk about also color. Colors are extremely important for any kind of graphics in scientific publications. So we'll talk about that. And we'll also talk about color, selection for color blindness. This is especially important for, creating some color palettes. So we'll dive into that as well. And finally, I'll give you a couple of free resources for maximizing your schemes. So I will try to not only show these slides, but also give you some examples and I will play with some ideas in real time. So I hope you guys find these useful. All right, so before we get started, let's just get an idea what a figure is. Because we can get different terms when we talk about figures. So figures basically are visual depictions, okay, that we create and we include in our presentations or scientific publications to guide the reader and to improve their understanding on what we have written. Okay. So we have two main types of figures. We have graphs, sometimes also called as plots, and these are used to present quantitative data. That's the main idea. We're showing numbers. We're showing quantitative data, okay? As we can see here in this plot, you don't need to worry about the contents of this figure and the labels here. But just here, we can see numbers. We are plotting numbers on the x-axis and numbers on the y-axis. So we're showing quantities, okay? Now, the other type of figures are called diagrams, schemes, or just images. And these, on the other side, these explain qualitative concepts, right? So here, of course, we may see numbers, but we are not like plotting any relationship, right? We're just showing ideas, we're showing schemes that are depicting a general concept, right? Or we're trying to explain like some steps. So that's the idea. A plot or a graph shows a relationship, right? We show numbers. And in diagrams, schemes, and photos or images, we're just showing concepts, ideas, representations, okay? So if we're talking about figures, we can talk about these two, okay? But if we're talking about graphs, we're only talking about the ones to the left, all right? Okay, so now which graph or which figure should I use? Well, we have a bunch of different types of figures. For the interest of time, in the interest of time, I will not cover all the figures, all the types of figures that we can use for a very specific scenario. Some of you may work with, uh, you know, um, earth sciences, so you will use maps, but maybe some of you guys work in statistics or natural sciences, so you care more about like bar plots or X, Y plots. So I will just stick to the most important ones, and I highly recommend looking at other resources that might be more suitable for your specific area. But we can use an infinite number of representations and an infinite number of graphs and plots and figures to show our data. But we need to find like maybe the most suitable for our purpose. And if you're thinking, okay, which graph is the best for my purpose? I would say that the best way to find it is just to think about causality. Okay, so what kind of information we want to show in our graph? So if there's a direct relationship between variables, probably the X and Y graph is the best one, right? And probably this is the most common graph. So notice here that it's a graph because we have numbers. There's a quantitative relationship, right? And here we're just showing, for instance, in this plot, how this variable, the electrode potential, changes over time, which is the X variable, the X axis, right? So this is the most common graph. And remember, causality here means that changing one parameter, changing one variable, for instance, the X variable, time, will change or will have an effect on the Y variable, on the electrode potential, okay? So this is a way to determine if this is the best one. Now, when we have other kind of relationships that are not there's no direct relationship between these different groups. We're just showing a value, a certain threshold or something. It's better to use a column or bar plot. So for instance, in this plot, here we're just showing the concentration in ppbs of different metals, right? So these metals are not related to each other, right? We're just showing this is the concentration of purified and impurified solutions. That's it. So in this case, in these cases, it's better to use just bar plots or other variants, like for instance, pie charts. In a pie chart, we're just showing the composition of a group, right? So in this case, we don't necessarily show any relationship. We just show, okay, from these set of, like maybe students, maybe only roughly 30% are interested in grad school, okay? So there's no relationship maybe with students interested in industry. So just think about causality. If there's a direct relationship, use XY graphs. If not, if there's no relationship, use a column or bar plot. Okay, these are the two main groups of graphs that you can find out there. All right, now I will give you very specific guidelines on how to create the best graph. And the main idea here, the main takeaway that I want you guys to remember, excuse me, remember after watching this seminar is that a graph, a very high quality and well-composed graph should stand alone, okay, and tell a story effectively itself, okay? So the idea is that if someone looks at the figure, it will be great if you can tell the story of the figure through the graph. Okay, if you don't need to, if you think like you need to add more detail to the figure, like, oh, I need to, the reader needs to look into a paragraph in the text to fully understand the figure. Maybe the figure is not doing its job effectively. Okay, so consider two main ideas. First of all, we need to worry about accuracy of the data. Probably this is the most important one. It doesn't matter if the figure is beautiful, if the data is wrong, if the data is showing something weird, if the data is not accurate, well, the figure is bad. That's it. Okay. So you need to make sure that the data makes sense, that your numbers are correct. That's the most important requirement for a figure. And second, we need to take care of the aesthetics of the figure. We need to make sure that it looks attractive, that it looks compelling. So because it's a visual depiction, so it needs to feel to make you feel, oh, this is easy to understand. I can easily understand what's going on. Of course, after making sure that the data is accurate. Okay, so therefore, graphs, notice that graphs in general need to be clear. So they need to be easy to understand, right? They need to explain themselves, okay? Figures or graphs must be precise and accurate, okay? And they need to be efficient. We don't want to put a lot of data there. We just want to put the data that makes sense, that tells the idea or the point that we want to convey to the reader. Okay, so make sure that every time you make a figure, you fulfill these requirements, that it's accurate, is compelling or attractive, and it needs to be clear, precise, and efficient. Okay, so for instance, in this plot here, we may not have a background on electrochemistry because this plot is a linear strip tomogram. But if you try to understand what's going on here, you can get some ideas. So for instance, you can see that we're plotting the electrode potential change against the current density. And we clearly see the units here. We see different scenarios. And as we can see here, it seems like something is changing. We're increasing the concentration of something. And if we look at this label here, we can see that, oh, we have 1 molar potassium hydroxide plus iron. And by looking at these colors, we can see, oh, so it is changing the concentration of iron in these measurements. Okay, we can see some labels that are telling us, oh, the scan rate, how fast we scan the potential is 5 millivolts per second. We can see that there is a control sample that is purified KOH. So I guess that this is 0 ppbs of iron, right? And we can see that there is a peak, and this peak represents this transition from nickel 2 plus to nickel 3 plus. So notice that I can get that information without knowing the context of this figure. I don't need to read the whole paper to understand this figure. I can get some ideas just by looking at it. So that's the main point of a figure. It needs to stand alone and tell your story as it is, okay? All right, so now I'll give you very specific guidelines. Okay, so first of all, make sure you always include the axis title with units here, as we can see here. Keep the font size readable. So make sure that the font size is consistent. Actually, notice here that most of the labels here have the same font size. Maybe only here charge and these charge labels are have a slightly smaller font size. But notice that it's not that different though, right? So you make sure that the font size is about the same in the figure. Don't use like too large and too small font size. Follow the golden rectangle rule. So instead of having like squares and like wide rectangles, most of the time we can use this ratio between the height and the width of these rectangles. So it's 1.6 ratio, which is this one that I'm showing you right here. So try to use these ratio consistently across your publication or your seminar, okay? Make sure you have axis lines, and it's typical to have the 4 axis lines, okay, not just 2. It looks better when you have 4 axis lines, and that also you include major and minor ticks. As we can see here, we have major ticks every 5 seconds, and we have minor ones every 1 second. So this is extremely helpful because, for instance, if you're looking at one potential here, you can easily tell that is 1.1 volts. But if you're on the other side, instead of having to look into the left axis, you can just go right and you can see the same coordinate, right? So that's why it's important to have all the 4 axes with major and minor ticks all the time. And make sure they are bold so you can easily spot these lines. Now, make sure you use a distinguishable and noticeable colors. We'll talk more about colors later. But here, just by having colors, you can easily tell a difference. You can see, okay, yeah, these samples are different because they have different colors, okay? Use legends and labels, especially labels, to identify different traces, different curves. So for instance, notice that here, by using these arrows here and these labels, we can easily identify, okay, this one is 100 ppb cobalt, this one is 100 ppb manganese, and so forth. So by having labels, like this one is telling you that this section of the curve is the discharge, this section is the charge step, having these dash lines here telling us, okay, this is the halfway potential, something like that. By having labels showing the experimental conditions, like, oh, this electrode is nickel hydroxide in 1 molar KOH. The experiment was done at 2.5 milliamps, and this are curves after 1600 cycles. So the idea here is that these labels add extra information and make everything easier. So you don't need to write down a whole paragraph explaining this figure if you just show this information in here. And sometimes you may have some blank space, like as we can see here. So in this blank space, you can put a label showing the experimental conditions as I did here. Okay, so that's another idea. Make sure you use labels so you can make everything simpler. Okay. And yeah, as I explained, make sure you use the empty space to your advantage. Sometimes we can use it by putting labels or by adding an inset. Typically, well, it depends on you, but like recently, insets are becoming less popular in articles, because when you add an inset plot, you need to make everything smaller, and that's not good because you're decreasing the font size. So I recommend this is my personal opinion, but I recommend not using inset plots. Okay, maybe you can add a scheme, you can add a chemical structure here, something like that will be great, but you don't necessarily need to add something to the blank space. But maybe the most, I would say the simplest or the most useful thing to do is to add labels showing the experimental conditions. Okay, more guidelines. So avoid symbols, or if you use them, define in the caption, in the figure caption. So for instance, here, what I mean by avoiding symbols is in the title, axis title, make sure if you have a space, make sure you include the full name. So here, instead of adding a B, and for us, B represents the binding energy. Maybe for someone who is not familiar with X-ray for electron spectroscopy, they don't know that B or BE refers to binding energy. So it's easier if you just write down binding energy. Okay, so it's better to do that. Don't just add, like, for instance, instead of current density, you just add a J letter. Instead of doing that, just add current density as it is. Okay. Sometimes you may add symbols like this in labels. So it's okay. For instance, this symbol here represents the Fermi energy or the Fermi level. So instead of writing Fermi level, maybe you prefer using the symbol. That's okay. Or here, this is the valence band maximum. So this is a quite long label. So we don't have a lot of space here to write down valence band maximum. So instead of doing that, you can just add VVM, and in the figure caption, you can just state that. You can say, like, EF refers to the Fermi energy level, or VVM refers to the valence band maximum. So you can do that in the figure caption. But here, make sure that everything that is shown in the figure is easy to understand, and if not, make sure you mention it in the figure caption. Okay. Be careful about some axes when you use logarithms. Logarithms don't have any units. Okay, so if you're plotting pH, it's just pH. It's not arbitrary units or anything like that. Like absorbance. Absorbance is the ratio of two intensities. So it's the logarithm of this. So you don't need to add any units there. It's wrong when people add like arbitrary units. No, absorbance doesn't have any units. Make sure you include error bars. And if you, for instance, if you have a bar plot, and if you do that, make sure you mention what type of error you're talking about in the caption, in the figure caption. So is this error bar representing the standard deviation or the confidence interval or the standard error of the mean? So make sure you explain what kind of degree of variation or error or uncertainty refers to, okay? The error bar refers to. Keep your significant figures consistent. So for instance, here, if you have like 15, 10, 5, 0, just keep all the sig figs consistent. Sometimes you may need to use scientific notation, so make sure you keep all your sig figs consistent. Also notice here that for the binding energy in these labels, I have 3 sig figs. So in this one should be 3, and here, I'm also keeping 3, 3, 3 sig figs, right? It's not like, oh, and this one is going to be like 3, and this one is going to be like 4.1, and this one is going to be like 3.2, 3.4, right? So make sure you keep all your sig figs consistent. Make sure that you always show the scale of the y-axis, okay? As in the previous figure, in the previous slide. But, sometimes you may prefer to just, just add a scale bar. And that's okay. Actually, sometimes you may, just like, for instance, sometimes people, instead of putting all the figures, all the curves at once, they create a stacked plot where these curves are shifted along a certain axis, okay? When you do that, it's better to use scale bars, right? Because the y-axis is not reflecting the actual intensity. And we'll talk about more about scales later. But the main idea here is that a scale bar can also tell you or can give you an idea of the units of the y axis. So in general, just make sure you always show this, either using the scale on the axis itself or using a scale bar. And as I told you, use labels, dash lines, grid lines to guide the reader. You don't necessarily need to add grid lines all the time, because sometimes grid lines look like make the plot look to look crowded. So you can use dash lines. Like for instance, here, just by adding one dash line at 0, we are showing, okay, the Fermi level should be 0, right? So you can guide the reader just by looking at this. By adding these lines here, we're showing the maximum, the peak maximum, right? So here, instead of like, asking the reader to guess what value this is, you can just put like 3.08, right? So here you're telling the reader, okay, this is the actual value of this coordinate. By having these a dash line, you're representing the maximum of this curve. Okay, so again, make use of dash lines, labels. Notice that here this arrow is telling us, oh, this valence band maximum is changing depending on the curve. And here we are putting the type of material that we analyze in order, like in a certain order, right? We can see that the one with iron is the first one. Then we have just nickel hydroxide. Then we have like nickel oxyhydroxide in darker green. And then at the end, we have the blue one, which represents the sample plus cobalt, okay? So that's another way to show or to guide the reader and tell the story. Okay, the story here is that these valence band maximum shifts depending on the material that we analyze, okay? And that's why we add the dash line at 0, so we can clearly see that there's a difference, and also the arrow here. About font size, be careful. Font size really matter, especially because sometimes when we create this type of plots, you may think, oh yeah, I can easily see what's written here. But what about these other labels? Maybe if you're watching this video, it's really easy, but imagine you're watching this in a seminar, in a conference room, and the screen is far from you. So that's why it's important to make all the font sizes consistent. Make sure that if you're using like 18 point size, for instance, Um, Make sure that you use something equal or quite similar in all your figures, schemes, diagrams, whatever you show. Because sometimes they're really small. Like sometimes these, like for instance, the scale here is really small compared to the scale bar here in these TM images. So think about your reader. Think about the type of audience that you have. If this is a seminar, that it's critical. Well, if you have a publication, a paper, it depends. Like some people may have issues, looking at your figures just because it's the font size is too small. So you just keep that in mind. So yeah, make sure it's consistent. Make sure you don't have like, the schemes are too crowded. Avoid avoid including a lot of text. And that's why, sure, you can include labels, but sometimes you need to be careful. Don't add too many labels, because if you do that, maybe you will risk your figure because you will be adding a lot of text in your figure. So just reduce the amount of text, okay? Just be careful and find a trade-off situation for your purpose. Um, Sometimes you can use the supporting information. Most of the times, it's really rare when people, when journals don't accept supporting information files. But if they do, which is likely, you can move some images, especially images, to the SI. Sometimes there's no point in including images in the main manuscript, because the images is just showing, oh, look at this geometry. It looks really nice. Great. But in your main manuscript, you want to show or highlight the main discoveries. So maybe you figure an image is not telling you like a lot of information. Maybe this one instead is really good, the one to the right. But maybe the one to the left is not the best. So you can use the support information also, because in the support information, you don't need to create, you're not restricted in terms of size. So you can, for instance, make this figure to occupy a single page. And by doing so, you will have a huge image that can be seen by the reader easily. Okay, so think about support information. Sometimes you may add schemes to the support information too, especially if they are too long, too complicated. So think about that. And also reconsider the format of your paper. Sometimes if you're writing a communication, well, you will be limited in terms of size. So, just think about it. Like, do I really need to include like a huge figure with 18 small graphs just because the communication has a limit of 3 figures? So I will just try to fit 30 figures in just 3 large multi-panel figures, right? So if that's the case, maybe your paper is not a communication. Maybe you should, aim for a full article paper. So just look at the journal guidelines and you will find um, the best outcome. Now let's talk about the scale, because the scale is extremely important, and the scale is extremely helpful because you can show the same data in different ways. So for instance, we can use absolute scale. The absolute scale is only meant to show quantitative information. And this is important because this means that the value is going to be the same. It doesn't matter if you do it here, if you do it in another lab or whatever, because this is a reproducible value. So you're basically putting the original values as they are from the instrument. So for instance, one example is the absorbance. The absorbance is proportional to the concentration. So if you measure the same sample here or in another lab, you should get exactly the same result. Now, there's also arbitrary scale, and the arbitrary scale it typically is used typically when the values may change because these depend on the instrument or the amount of sample. One typical example is XRD patterns. So, excuse me, typically the intensity will change depending on the sample or the instrument. So typically in an XRD pattern or in an FTIR spectrum, you don't care that much about the intensity. Typically, you care about the peak position, right? Or the width, something like that. So use an arbitrary scale if you care about the qualitative information rather than the quantitative information. And typically these values cannot be reproduced. Like sometimes, for instance, the intensity may depend if you're pressing the sample against the sample holder. So if you change that from instrument to instrument, you will get different intensities. But again, you don't care about the intensities, you care about the peak position. So you use an arbitrary scale instead. So for instance, in this example, the red curve to the left is showing the absorbance. So this is an absolute scale, right? And the blue one to the right is showing an arbitrary scale. So here, notice actually that the intensity is plotted in arbitrary units. So this is basically telling you that we don't really care about the intensity, but we care about the peak position. So we care about this peak because it's at C100 nanometers by looking at the wavelength here axis. In the absorbance, we also collecting the absorbance, across these wavelength numbers. But the idea here is that on the left axis, we care about the intensity. And on the right axis here, we care about the peak position. So think about the type of scale that you need depending on your measurement. We can also show the scales as a relative scale. So typically we use this when we have multiple curves using an arbitrary scale. So we don't care about the intensity. But all these curves were done or performed under the same conditions. So we want to show some change relative to a certain curve, maybe the initial one, maybe the control sample, something like that. So yeah, we typically use one curve as the standard, as the comparison curve, okay? The other type of scale is called normalized. So what we do here is that we use a normalization factor that changes for each curve. And we use this factor to normalize or to represent the intensity, maybe the same intensity for all the samples, to compare peaks. And it's important that you always specify what's your, procedure for normalizing this. Are you dividing this by the intensity of the control sample, the first sample, the last sample? So it's important to always be specific. How are you normalizing the scale in this plot? And you can show that in the figure caption. And notice that these two typically are used to establish trends because you can get an idea of what's going on. And also notice that these are unitless as if you're calculating a ratio. So if you are getting a ratio, you don't need to specify arbitrary units. No, because in this case, you have a ratio, so the units cancel out. So for instance, here in this example, we see two different kinds of curves. So which one is relative and which one is normalized? Okay, so we can get some ideas. So in this one here, notice that all of them are showing, all these curves represent different times. But notice that here we're trying to see some change relative to maybe this one, because this one has a one unit of intensity right here. So maybe in this case, we're comparing these. In this other one, notice that all of them have the same intensity. So that means that somehow we had to multiply or divide the intensities of these curves by a certain factor to make all these the same height. So that means that the one to the left has a relative scale. We're just showing the intensity of these curves relative to the first one, to the one at 0 minutes, right? And on the other side, and on the normalized scale to the right, we're showing all of them under the same intensity. Of course, they do have different intensities, but the idea here is that we divide them or we multiply them by a certain factor to get all of them to the same intensity. And notice that here we don't have units, it's normalized to max, right? And this one is relative. So it's 1 because it's just 1/1. This is the standard that we are using, right? So here we don't use units. And notice that in these two, we use these plots to show trends. So on the left one, we show that the intensity decreases over time, right? After 55 minutes, the maximum intensity is like below 0.1. It's like below 10% the intensity of the first one, right? On the plot to the on the right plot, we see that there's a peak shift. We are normalizing the intensity so all of them can be compared. But here we see that there is a change in the wavelength, right, after 55 minutes. So there's a shift to longer wavelengths. So notice that we are showing two different trends from the same data. The only thing that changes is the way we show the plots, and this is done by changing the scale. Also, make sure you manage the amount of data and information that you show. Just don't just put a lot of information in your figures. The main idea here is the less shown, the better. Notice, for instance, in this figure, if you ask someone, hey, could you please explain me what's going on here? Well, a lot of stuff is happening at the same time, especially if you're not familiar with batteries. Or impedance spectroscopy, electrochemical impedance spectroscopy. It's really hard to understand what's going on here. So just don't just put a lot of raw data in your figure. Just make sure you use the information that you need. So in general, avoid multiple panel figures unless you definitely need to do it. Because, by having unnecessary data, you're diluting the main idea. So for instance, these insets here, I don't know what they are explaining. So maybe by having these insets here, or by having certain plots, like I'm not getting anything useful from them. So avoid that. Avoid including figures that are just diluting the main idea. Okay. Notice that by having multiple panel figures, you need to decrease the font size. Also, your figure caption will be longer, so it will be almost like a short paragraph instead of a couple of sentences, right? And also by having these multiple panel figures, sometimes you may overlap or have some scales or something very close to other plots, so they may overlap and they may confuse the reader. So be careful with that. On the other hand, single panel figures have advantages because you will emphasize only the key finding, the critical idea that you want to show to the reader. And readers will, get the idea quickly instead of having like a multiple panel figure that is extremely confusing. And of course, a single panel figure is clear, is straightforward, and also the captions will be shorter. Okay. So now talking about figure captions, here also you need to be careful because the figure caption needs to be connected, of course, to the figure, and you need to make sure that is also, resonating with the story that you're telling in the figure. So sometimes people and when you're reading a paper, typically you don't want to switch between the figure and the main text a lot of time, right? You just want to look at a figure, understand what's going on, understand the experimental conditions, the experiment, whatever you're doing. So make sure that you also use your figure caption to add more information. But again, be careful. Don't just make it very crowded. So for instance, the main rules for writing figure captions is just use the first sentence to just describe the main idea of the figure. What's the idea the figure telling you? or you want to tell the reader, okay? Include experimental conditions or make sure you clarify some aspects, like for instance, as I explained previously, error bars, if you're doing replicates, if a symbol needs to be defined, something like that. Define symbols, as I said. Also describe any labels or insets if you're using. And of course, make sure that the caption matches the figure you're talking about. Sometimes we copy and paste the captions when we're writing, so be careful on that. And as I told you, when you use like multiple panel figures, you will end up with a huge figure caption. So it's almost like a new paragraph, and it's confusing. You see a lot of symbols, a lot of letters here. And also the figure itself is really complex. So that's why I try to make use of single panel figures instead of multiple panel figures if possible. Also, another term is using table of contents images. So table of contents are really important because basically these are the first look at your paper. So for instance, I will ask you, what influences whatever decision when you go to a candy store or a supermarket or you want to get clothes? Well, of course, we will say, oh, I love chocolate. I don't care about the other candies, but I love chocolate. But we need to understand that we are humans. So inevitably, humans are guided by aesthetics, right? If something is good looking, if something looks compelling, we'll feel more attracted to it. So that's why the first impression of your paper is critical. And this impression usually comes from two components of the publication, the title, and we can discuss about the title in another talk later. But the second and also equally important is the table of contents, also known as graphical abstract by some journals. So the TOC basically is a message, a visual message, okay, that basically tells the story to the reader before reading the paper. And notice that it needs to be graphically appealing and it needs to be clear so the reader can understand the message rapidly. Okay, so this table of contents is critical. So don't think, please don't be like, oh, okay, so my manuscript looks great, and then you don't have a TOC. Your TOC may make the difference, at the end of the day, because if people don't look at your paper just because it doesn't have a TOC, it doesn't feel compelling to the people, maybe you will get less citations just because your paper, even though if your paper is the best one, is not, getting noticed by the audience. And so when you have these TOCs, just think about the message. So for instance, let's think about these TOC here. What's the intended message here? So you can pause this video and just think a little bit about it. Try to, play around and say like, okay, I don't have any background on this paper. I don't know the title, but I can get some ideas. And now I will tell you what are those messages. So for notice here that we have two images. These images look different. So we can say, okay, we have a some different composition here. Actually, these are quantum dots. We can see that these samples have these like red or orange bright color. Notice that these is critical because this is telling us that we are changing these somehow by having by requiring just 3 minutes. And this stopwatch here is critical because also it's telling us time. And typically a stopwatch is used to measure something that is fast, right? Well, if we look at the title, look at this. Flash synthesis of cadmium, selenium, cadmium sulfide, cadmium selenide, cadmium sulfide, core shell quantum dots. So notice that here the idea is speed. This is the main takeaway from the table of contents. And this is the focus, the center of the story. So the key here is adding 3 minute, right? And adding the stopwatch. And by adding these in between these two, you can say this is fast, right? So that's the main idea. Make sure your TOC does something like this. So some best practices when making table of content images: make sure that it's simple, it's concise, and it's clear, straightforward, straight to the point. Ensure that it resonates with your title. So notice here, flash synthesis resonates with the stopwatch and the 3 minute label, okay? So it needs to be like, it needs to complement the title, okay? Use color cartoons. So here the idea is that it needs to be compelling. So make sure that it's attractive, visually attractive. Stay away from complex schemes. Don't add like multiple panels, like 6 different figures or schemes that are too complex, because these will only confuse the reader. So make sure that this is clear, it's concise. Don't do this. Some people just copy one graph, like, oh, this is the best graph, the best figure from my manuscript, I will use it as a TOC. Don't do that. The idea is that you use the TOC as an extra figure, okay, that shows your main idea, the main story in your paper. So don't do that. Spend some time for creating the TOC and make sure that the TOC is complementing your title. It's not just another figure from your paper. And also follow the journal's requirements. This is important because some journals require certain sizes. Typically, it's horizontal orientation, but be careful here so you don't have to redesign your TOC after submission. Now let's talk about color, and this is the last section, just talking about colors, because colors are really important. So having a good set of colors will definitely make the difference in when you make figures and in graphics. So we'll talk about color palettes, because color palettes are extremely important. By selecting these colors, we'll show sometimes trends, we'll show different samples, something like that. So I'll talk about different types of color palettes. So we have first qualitative palettes, right? So qualitative palettes have distinct colors. So we use these palettes to show categorical variables, okay? So for instance, if we have these colors here, these are different from each other, okay? So we use examining something qualitatively. We also have sequential palettes. So the idea here is that we use the same color and we just change the lightness or the hue, okay? And we use this to show some order or change of the same sample, for instance, over time or at different conditions, something like this. So use it for ordered variables. And then we have diverging palettes, and these are used when we have central values, like something in between. Like, so for instance, something is like really hot and really cold. So we have to pass through something that is in between cold and hot. Okay, so we have two different colors on these two ends, and they kind of merge in between. Okay. And we can also have discrete or continuous palettes depending on the number of variables. So for instance, if we have like 7 different curves, we may want to use a discrete palette because we have 1, 2, 3, 4, 5, 6, 7 colors. So each one represents one curve. But if we have like 1,000 curves, it's better to use a continuous palette, because by doing this, we'll have a smooth transition from curve to curve until eventually we reach the other end. Okay, so in this case, notice that this is a discrete palette, this is a continuous one, but all these two are both a diverging palette because we have two ends on these. Or in this case, a specifically case is sequential, right? This one is diverging. These are sequential because we're just changing the hues and the lightness. All right, so well, let's give us a couple of examples. So for instance, this one, and can you guess what kind of color palette is? So notice that here we go from a light brown and then we have a dark brown. So this is a sequential one. We're just changing the hue or the lightness of the same color. What about this one? So we just see two different colors. So that means that this one is qualitative because we just have red and blue. So these are different. Of course, one goes after another after activation, but these are two different colors. We're not changing the lightness of the blue. We're just having another color. What about this one? This one has three, four, like kind of four different colors. So we may think, okay, this one might be qualitative. Initially, the idea here is that this one was a diverging palette because it goes from 0 to 20,000 cycles. But I think here, even though it's a diverging because we go to like a midpoint, in this case, this kind of trend will fit better with a sequential palette instead of diverging. So if we have the same like here, like going from 0 to 20,000, having the same color, but just going through, a change of lightness or hue will be better. So yeah, so that's why sometimes you need to pick the best type of color palette depending on what kind of, change you want to show. All right, so now some tips for using your color effectively. Don't use a lot of colors. Sometimes if you, for instance, if you have all this data, but you care only about these two groups, just you can gray out all the other ones and just keep these two colored. And that's it. This is better. So avoid unnecessary use of your colors. Follow color conventions. So for instance, sometimes if you're using chemistry, well, you know that according to some standards, some elements have certain colors, so you can follow that. Sometimes, I don't know, maybe a certain kind of, I don't know, measurement, whatever, you feel that it fits blue, well, keep using blue consistently throughout your paper for that specific sample, for instance. So yeah, this is what I was trying to say. Just make sure that these colors are consistent. So for instance, here in this plot, I'm using, for instance, blue for cobalt, and in this other plot from the same manuscript, I also use blue for cobalt. So that means, oh, if I ever see blue in this paper, it refers to cobalt. Okay. Use contrast to your advantage. So notice that if you're having, if you use a font that is, for instance, light, like in this case, white, use a high value contrast. So use a dark contrast. And the opposite here. If you have black text, have a light contrast. When you have the opposite, like when you have like dark contrast and also dark text, it looks, it becomes really hard to read. And also be careful when you have backgrounds, patterned backgrounds or complex backgrounds, because sometimes you may have issues with this. And I will show you a couple of examples later on how to improve this. Now, this is a very important topic. It's color blindness, because it turns out that about 4% of the population, global population, have some sort of color blindness. So there are three main types of color blindness. Red blindness, so basically people suffering from protanopia, they don't see red color, so they just see like brown, like between orange and brown here, and blue. Uh, Green blindness or deuteranopia, they don't see green. So here again, they see this kind of like, transition just between like brown. And trianopia is blue blindness. So people suffering from this illness, they just see like red, green, but they don't see blue. Okay. So notice here that there's a pair of colors that can be always distinguished. Okay, maybe some people, they don't see that color, but they can distinguish it, right? And these two colors are red and blue. Because notice, for instance, here, people with protanopia, they see blue, they don't see red, but they can distinguish it because there is a color change here. Or people suffering from blue blindness, they don't see blue, but they can differentiate this like gray color here from the red. So that means that red and blue are typically friendly. You should use them. On the other side, what color is the least colorblind safe? Or in other words, which one is really hard to distinguish for all these groups? Well, the answer is green, because notice that none of these guys can see effectively green. So for instance, if you have protanopia, you won't see a clear difference between red and green. Also, people with trianopia, they kind of see the green, and they may see a little bit of a difference with blue, but it's not as strong as red and gray here. So that means that we need to consider these colors. And also, it turns out that about 99% of all colorblind people, they will suffer from protanopia. Okay, so blue blindness and green blindness are not that common, but still we should consider that when we make our color palettes. So in general, notice that we should avoid using red and green all the time. Red and green are not very color friendly, and the best combination is red and blue. Okay, so use red and blue in your color palettes. Now I'll give you some guidelines on how to create your color palette, and especially being colorblind safe. So here, for instance, notice that you can play with the saturation and hue for red and blue. So for instance, just by using these two, red and blue, but having different shades or different saturation levels, you may address all the issues all the issues for every single color blindness problem here. So that's a strategy. Just play with red and blue tones. And you should avoid these combinations whenever it's possible. Avoid red and green, green and blue. So notice green is the common color here. But you should also avoid other colors like gray, brown, and black, because as we saw in the previous slide, people suffering from, for instance, red blindness, they don't see red, they see some like gray or brown color. So you should avoid like having these colors combined with red or blue, okay? Second one, use highly contrasting colors. So even if you suffer some color blindness type, contrast is not an issue. So for instance, here we have a TM image. Well, there's no issue by looking at this white scale bar here, because we have a dark contrast, dark background. So we have a light scale bar, light color scale bar. Or also with Jello. Jello is light, so the background is still dark. So that's better. And this actually doesn't show any problem for colorblind people. When you have complex backgrounds, you can add a certain like glow around the letters, around numbers, around figures, or around like shapes. So by doing so, you can manage the background in a better way, and you can create this contrast, right? And also notice that here, by having just different shades or tones of green, you have light green and dark green. So you should not have problems, because you're using the same color, you're just changing the contrast and using white here because you have a dark background. But here you have a white background, so you can add a dark green inside, so you have contrast. All right, use patterns and textures. By using this, you may solve issues. For instance, if we have blue and green here, you may have issues because this is not colorblind safe. But by having patterns, you can easily identify each one of them. Or if you use a sequential color palette here, by having this pattern here, you can easily identify them, these differences. So notice here that by adding this pattern, you can, instead of having a shade here that will overlap with this red color here, you may just add a pattern, so that makes everything easier. Also, try to use symbols, labels, dash lines, whatever improves your curves. So these are extremely useful because these speed up the color recognition process. So for instance, here, if we have a legend like this, even though this color combination is somehow colorblind safe, notice that we need to look at the blue and then find the blue curve here. For people suffering from color blindness, it's gonna take a while because maybe some of them won't see the blue, they will see just brown or gray or something like that. So by having a label right next to the curve, everything it's easier because now it's like, I don't care about the color. This curve is right next to the blue label. So piece of cake, right? This is even better if we have a dash lines, different dash lines. These guys have different, sizes. So here it's easier because we can easily identify which one is which by having the label and the dash line. Or instead of dash lines, we can use symbols. So by having this symbol, we can track these symbols, even in this area where everything merges and entangles. So yeah, use other combinations of symbols, labels, dash lines to make sure that your reader can easily understand whatever trend or find the curve that you want to show. So notice here, for instance, for these bar plots, instead of having like these borders here, like if someone's suffering from color blindness, red and green, they're not very friendly. But by having a white space in between, they can easily detect, oh, there is a separation or a border between these two colors. So these are separate data sets, but data sets. But maybe for people with color blindness, they will have trouble finding a difference between these two. Also, you can go monochromatic. Like for instance, if you want to use brown, that's okay. Brown is not maybe very color blind safe, but if you only use different tones of brown, well, that's not a problem. If you create like infographics or other kind of compositions, just change the colors. So you can make your figure blue only and you can show the same information. Notice how here these guys created these logos, but in different tones of blue, so that everything makes easier. So this is especially useful when you have sequential color palettes. And you can also create your own color palettes, and I will show you some resources later. But notice that you have limitless combinations. For instance, this is a New York Times color palette. So you can basically play around with different hues, different saturations, and you can create your own color palette. There are also some color palettes available in the literature that were specifically created for scientific publications. So take a look at this. You can just Google them and you will find them there. So you can use these. And also I will show you some resources to create your own palette. So for instance, here, let me stop the share, the presentation, and I will show you these resources. So the first one, it's called Data Color Picker. So let's go here. Um, yeah, this one here, data color picker. So this one is pretty simple. So the idea here is that you can change the number of colors, 4, 5, 6. You can check the background. So if you want to change the contrast. So here, notice that here we can click on the color and select whatever color we want to use. And here we're creating a palette. So we can only change the ones to the colors on the ends. So for instance, here we can create a diverging palette, right? Because we're going from one color to another. So we create different combinations in between. And we can change the number of colors. If we want to just use a single hue, we can click here and we'll have a sequential palette now. So here we cannot modify this one. We can only modify the first one. So if we select green, we'll have different tones of green. We can change the color intensity or the brightness, right? So we can have just dark and or bright and, right? And here we can copy the hex values, which are really useful when we want to use this in other programs. I will show you how to do that at the end. Also, we can create divergent palettes here again. But yeah, the idea is that this is a very straightforward and very simple tool. The next tool, it's called Chroma JS. This one is also to create palettes. Here we can change the number of colors. So if we have just if we just want 5 colors, we can add so many colors here. But if, for instance, if we just want like 2, we can manually delete this one. We will have 2. And by clicking here, we can see these, you know, palette selector. So we can change different hues, different saturation, different lightness. So for instance, just by clicking here, we can find different hues. For instance, if it's like, yeah, I want to find another color, like more like maybe red or something like that. So if we go back here, we can find different tones. For instance, let's say like this one, red. So now we have another palette. We can select if we want diverging palettes, if we want to change from this side to this side, or just sequential. Here we can just, you know, delete these. So we'll have just a sequential palette, just like one. But the cool thing about this one is, for instance, let's do an example here. Let's select a palette that is like red, or actually we can just type red. Well, maybe not like this. Let me just copy one of these here. And then let's find it. Like something like this. And let's have here a green. Okay. So something very important about this tool is that it's telling us if the palette is colorblind safe or not. So for instance, notice that this is how a normal people, someone who's not suffering from color blindness will see it. But if someone has deuteronomia, they will just see brown tones, or, you know, um, green blindness, blue blindness. So this tool is extremely useful because it tells you if it's safe or not. So you can use this one if you want to check that. For instance, as I told you, the best combination is maybe blue, right? So we can play with different hues, different saturations, blue. Yeah. Okay, so this palette is colorblind safe. So notice that if someone has deuteronomia, we can distinguish between these two. We can still distinguish these two, and we can still distinguish these two. So this is a great tool to find colorblind safe palettes. Okay, and notice here that we can also extract these hex codes. So for instance, here we'll have 7 colors. So each one of these represent one of these colors here. So if we want more colors, we can just increase the number of colors here like this. And we'll have all these codes here for colors that we'll copy later. The second one is this one called Viz palette. So again, here you have 7 colors. You can add more, or you can decrease, you can delete here the number of colors. By clicking here, you can change the different types of colors. Here we have the hex code for this color. For instance, let's update it. And here, the cool thing about this tool is that you can see different examples of how your color palette looks like, or you can also see if there's any kind of issue with color blind people. So for instance, here by changing this, you can see, oh yeah, it's not a big deal for this color palette. And also another cool thing here is that you can copy these colors from Chroma, come here, paste it, and hit replace. Well, maybe too many colors. Let me just copy maybe this one that is line. Maybe that's the issue. There you go. So here now we have all the colors that we imported from Chroma. And here we can see how it looks in different examples. We can see if we'll have color blindness issues. It seems like it looks great. So we can use it. And notice another advantage of this one is we can convert the hex codes to RGB, which is red, green, and blue. So here, these are like coordinates, red, green, and blue. We can also use them in Excel or any other software where we can modify the colors. So there's also another tool, this one here, which is a converter. So for instance, if we select this hex code here and we convert it, we can get the RGB code that we can use for any other software, okay? And these are the standard color tables, okay? So yeah, this is another tool that we can use, really helpful. Another tool that I want to show you is this one. It's called Color Thief. So for this one, if you have a photo, figure, whatever, you can drag the image here. Then something like this will show up. And if you click here, you will get the color palette. So if you take this color palette and then you extract these colors, you can use them in your own program. I will show you this later with Inkscape. This is Inkscape. This is a tool that I use to create figures, and I will talk more about it later. But for instance, let me show you how we can do this. So if we go to this color palette, for instance, we can just copy this. We can copy this and paste it here, right? So we have our color palette. We can take a picture or a screenshot. And then, for instance, if we create a figure like this, we can just take a sample of the color using the dropper tool. And we can, for instance, okay, I want this like kind of violet or red. So now we have it here. And notice here that in Inkscape, if you go to the fill color here, we can get the code, the code that we can use for palettes. So for instance, if we copy this here, we can copy and we can use chroma or whatever here to create more palettes, right? So here is the color. So you can basically switch from one tool to another. You can export these hex codes, or you can use the color wheel, different resources to change the colors. But the cool thing about Color Thief is that you can take the color palettes even from your photos. So that's really nice, especially if you find a color palette from another plot that you like. Now, another tool that I will show you is a tool that you can install. It's free and you can install it in Origin. Origin is not free, but it's a lot of people use it for plotting. But this one enables another option in Origin to create color palettes. And after you install it, you can download it here. You just need an account. And I will show you here, having in Origin this file open here. And I will show you how this app works. So for instance, here in apps, you go here, after installing it, you have this color editor and you will have something like this. So notice that here we have the red, green, and blue coordinates, okay? So that means that here we can go, for instance, to this palette, and here we have these combinations, right? So for instance, we have 14100. So if we go to Origin, it's like 14100. So we have red. Again, we can just copy or do it manually. I just want to show you a couple of colors. I will just go to the maybe some colors in between, like this. And so here, let me just copy these. 130 and 250. Right? So we have colors in between. I'll just add one more. 0, 57, 111. Okay. So 0, 57, 57, 111. Yeah, so we have this color palette here. And notice that we can add more colors here. Of course, if we want a sequential palette, we need to put them in order. But if we have like 10 colors here, for instance, we can do something like going to Excel and change the the text to columns so we can copy these faster. We don't need to do it like one by one. But then once we do that, we will have a color palette here. So the cool thing is that we can save it and we can just add a name. So this is like example one. And this is our custom color palette. So now we close it. We can just hit delete. Here in Origin, if we want to change this color of this figure here, I'm using right now this color palette. So I will change to, I will keep it at a stretch. But here, if we click here in these 3 points here, we can right click in the color and load a palette. So nice here that now we have the one that we created. So we click example, right? Click OK. And now we have these color palette loaded here. So if we hit apply, now we have this transition. So now notice that this is some kind of like divergent palette. So we go from blue to red and we go in between these colors. Of course, if I add more to the, or add more colors in between, we'll have a smoother transition. But the idea is that now you can create your own palettes. You can, for instance, if you use Color Thief, you can take the color palette from another one, or you can create your own, check if it's colorblind safe. And now you can copy these codes, or you can use this converter to find the red, green, and blue, or just use this palette, copy from here, paste it into your color editor app, and that's it. Or if you're using other tool, like for instance, Inkscape, here you can paste the hex code and you will have your color palette here. And you can use it for all your figures. You can keep it consistent. So this is amazing. You can do a lot of things, just changing colors. If you want to change a specific colors like this, right? You can look at your palettes and other options that we have in Origin, or also in Excel or even Word. All right, so moving on, I just want to show a couple of things for creating schemes. So you can use Inkscape. As I told you, Inkscape is a tool. It's free. It's open source. So you can use it for creating 2D images. If you want to create like 3D looking images, you need to play with shadows and things like that, but it's extremely powerful. So I really recommend using Inkscape. For creating 3D graphics, you can use Blender. It's also open source, so it's free. And this is what people typically use for creating like this kind of amazing 3D renderings and models of the DNA and things like that. Now, we don't have a lot of time today, so I would recommend that if you want to learn more about Inkscape or Blender, just use YouTube. There are a lot of tutorials. I remember my first tutorial was like, I want to create an atom. So I want to create a sphere, a 3D ball. So I just went to YouTube and I was like, okay, how to create a sphere in Inkscape, and you will find videos. So just do that. If you do that, you can create, you can learn a lot of ways to create specific shapes, or how to play with lighting, how to play with colors in Inkscape. You will find tutorials on it. Also, for Blender, I strongly recommend watching the videos from the Blender Guru. He has amazing tutorials for beginners, explaining like, basic modeling, lighting, shadows, 3D rendering, all those options and opportunities from Blender, even animation. So go there and you'll find a lot of useful tutorials on how to use Blender. And I will go really quick here. This is just to test your new skills. If you want to practice, I suggest pausing this video, try to think first, and then you can look at my responses. Maybe I will not cover all of them, but use the all the learnings from these seminars so you can improve your skills for figure making. So for instance, in this figure, what are maybe the not so good looking aspects of this figure? So just think about it, and I will tell you now what's wrong with this figure. First of all, you should not use symbols in the axis. Here, instead of E, you should put like electrode potential. Here, maybe we don't need to use grid lines. Grid lines are, uh, like, saturating the figure. It's crowded. Also, the font size is not very consistent, so these are quite small, these are slightly larger, so make sure that it's consistent. Also, if you add like these kind of labels, these labels, I don't know what's going on here. So maybe one option could be mentioning these in the figure caption, like 1C represents this, 2A represents that, something like that. Also, the major and minor ticks should be inside, not outside. So just do that. And also good things. Well, also the colors here might not be the best. This one is too light, so I will just go for something like red, blue, and something in between, something like that. Now, about good things on this figure, labels are really nice. You can use arrows to show the direction of the scan. You can use labels to say, okay, this one is 50, this one is 100. We have experimental conditions here, which is great. We have a blank, and we're telling the reader this is a blank. That's why we don't see peaks. The inset, I'm not very a big fan of insets, but here the inset is not really bad because we're having a quite similar font size. Um, but yeah, the inset itself is not telling us anything unless you describe it in the figure caption. Okay. Right. What about this figure? Okay. So good things about this figure. We have experimental conditions. Um, Here we don't use units for logs, which is good. Notice that the units here are from inside, which is the current. It's the log of the current. And the current, of course, has units, but not the log. Okay. Um, we can see, for instance, that the font size is roughly consistent. That's good. About downsides of this figure. Again, we should not use symbols, or if we do, we should explain in the figure caption what does this mean. Maybe here you can add current density inside. We have plenty of space here. Again, that's why the inset is not very good, because here again we're using symbols, so don't do that. Also, we're using a lot of colors, and these colors don't represent anything, like, after all. So maybe here we don't need to have like this kind of variety of colors. Also, we have a lot of text, like writing slope equals the number. Maybe it's too complex. Maybe we can just add a number right next to each curve. And in the figure caption, we can specify, okay, the number right to the data shows the slope, something like that. So yeah, some suggestions on this figure. Okay, what about this one? So this one is a multi-panel figure. Maybe it's not extremely crowded, but I think it's better if we just show a few of them, not all these 6 figures, especially because these two at the end, they are multiple figures as well. So avoid multiple panel figures. Colors are okay for these because we're using red and blue. Maybe here this one is slightly, maybe it's not the best combination, red and green. Still, these are different plots, so we're not having them right next to each other, like, so we can easily differentiate between these two. But again, try to avoid red and green as far as possible, as long as possible. Um, Good things, we're providing labels, so it's easier to differentiate which one is which. In some cases, we're not giving that much information, so that's not good. But in other cases, it's like good to have some ideas. Again, symbols, you should avoid symbols in the labels. Good thing, pH doesn't have units, so that's great. In some other cases, maybe this is too long, so that's why we definitely need to add a symbol, but make sure that this symbol is explained in the figure caption, okay? What about this TOC? Okay, so bad things about this TOC is too much information. Even some diagrams are really small. The font size is extremely small. We can't see what's going on here. We have a lot of information. We have reactor design, this scheme, this other scheme, this optimization, this plot, and actually this plot is shown in the paper. This one as well, and we have a title, so we'll have a lot of text. So don't do that. It's not a good idea here to include so much information. What about this other TOC? So in this other TOC, it looks better compared to this one. We have, okay, we have some text, but these are like, consistent in terms of font size. We use figures, shapes, schemes to show, like, for instance, maybe this stopwatch is telling us that this is fast if we don't know the background. Of course, if we look at the title, we'll get a better idea. For instance, in the title for this paper, it says um, flow rate electrodeposition. So this symbol here represents the flow rate. So maybe by looking at it, it's not very straightforward, but in combination with the title, you can get a better idea. By having this scheme, we can see that this material is bifunctional, that it works both for the OER and the HER. And we have an idea of the chemical composition. We have an idea that this is a 3D printed flow cell. So this is a better TOC compared to this one. So in summary, I hope that this seminar was useful for you to understand the importance of figures and how to improve their performance. So again, figures are ways that we use to guide the reader, so the reader can understand all the quantitative and qualitative data in a better way. Excuse me. Notice that graphs show accurate data. That's the most important thing, but they must be visually appealing because that's how we will catch the attention of the reader. Make sure you use proper font size, use the right scale type depending on what kind of trend you want to show. Don't just put a lot of data there. The less shown, the better. Make sure that you have only the information that will tell your story. Um, Also, make sure that you spend a decent amount of time making your TOC graphics because the TOC is the first impression of your paper, and especially make sure that it resonates with your title. You can also find the best color palette for your needs and make sure, especially this, make sure that it's colorblind safe. And I show you some tools to do that. So use these tools and also the open source software to editing figures, 2D and 3D figures to improve and enhance your graphics. So I would like to finish this seminar just by showing this quote that I really like. And notice that it's not about the number of figures or how much data you show in your publication or in your seminar. Okay, that doesn't matter at all. The real thing that matters is how the results are delivered through figures. So think about that. Don't just add a bunch of figures and information, a lot of text and a lot of insets and schemes. No, 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 no. Try to make sure that your story can be easily understood by the reader. Okay, so this is the most critical point in the manuscript. And with that, thank you so much for your time. I'm sorry if this is quite long, but yeah, I try to show you a lot of guidelines and resources. Feel free to reach out. We in the UT Austin ECS chapter, we will be more than happy to help you. If you have more specific questions or if you want some advice on how to create figures or how to improve or maximize your paper, feel free to reach out and we'll be happy to help you. And again, thank you so much for your time and I will see you on the next time.